Okay, so in this video, we want to consider two examples of finding the tangent line to a function. The first example using or taking a trigonometric function. Our second example will be with an inverse trigonometric function. So we want here the tangent line to the function y equals tan of x over 3 at the point x equals pi. So first, let's find the y coordinate of our point. So the y value at x equals pi is equal to tangent of pi over 3. Now if you remember here, tangent is sine over cosine, so this is sine of pi over 3 divided by cosine of pi over 3. And these are familiar angles at which you should be able to know the value of sine and cosine. So if you remember, sine of pi over 3, that is root of 3 divided by 2, over cos of pi over 3 is 1/2. Well, we have root 3 over 2 on top. And if you divide by a fraction, you multiply by the reciprocal, so you multiply by 2 over 1. You can cancel the 2 over 2, and you're left with root 3 over 1, which is simply root 3. And so we have now the point on this function. The value of x is pi, the value of y is root 3. So here's our point. X equals pi, y equals square root of 3. Okay, so now we want the equation of the tangent line. So of course it's just a line, y equals mx plus b, and m is the slope. And if you recall, by definition, the derivative is the slope of the tangent line. So let's find the derivative of our function. So we differentiate with respect to x the function tan of x over 3. We have a composition here of two functions. The derivative of tangent is secant squared of x over 3. That takes care of the derivative of tangent times, by the chain rule, the derivative of what's left over. But this is just a third times x, so the derivative is quite simply 1/3. And we can write this, if you want, in terms of sine and cosine. This is 1 over the 3 here, and secant is 1 over cos. So secant squared is 1 over cos squared, so we'll have here over cos squared of x over 3. And this is now the derivative of the function at any given value of x. Well, we want the derivative specifically at x equals pi over 3, and this will give us m. So m is the derivative of the function at the point of interest, which is pi. Well, here's our derivative, and we are now replacing x by pi. So we'll have 1 over 3 cos squared of pi over 3 well, if you remember just a few seconds ago, we noticed that cos of pi over 3 is 1/2. So if cos of pi over 3 is 1/2, cos squared of pi over 3 is a quarter. So we'll have 1 over 3 times a quarter. But that's 1 over 3/4, and that's just equal to 4/3. And so now we have the slope of our tangent line. At pi, the slope is 4/3. So we can now substitute, and the tangent line has an equation given by 4/3 x plus b. And finally, we can solve for b using the fact that the tangent line passes through the function at this point. So the point x equals pi, y equals root 3 is a solution of the equation. So if we substitute y for root 3 and x for pi, we get the following equation. And then we can simply solve for b by doing root 3 minus 4 pi over 3. And so there you have it. We can right now write the final answer. So the tangent line is equal to 4/3 x plus b, and here's b, root 3 minus 4 pi over 3. If we wanted to, we could put everything over 3, but that is really just optional. You'd have 4/3 x plus, if you want this over 3, multiply by 3 over 3. So you'll have 3 root of 3 minus 4 pi all over 3. And that is the equation of the tangent line. So it really doesn't change anything that we have a trig function. The only difference is you have to know special values of sine and cosine. Let us now consider a second example, now involving an inverse trigonometric function. So same question, we want the equation of the tangent line to the function y equals, and now we'll take the arc sine of root of x and we want the tangent line, say, at the point x equals 1/2. Well, before we find the equation of the tangent line, let us first find the corresponding y value. So y at x equals 1/2 will be equal to arc sine of the square root of 1/2, but that's just arc sine. Well, the root of a quotient is the quotient of the square roots. So this will be square root of 1 over square root of 2, but square root of 1 is just 1, so we have 1 over root of 2. If you prefer, 1 over root 2 is the same as root 2 over 2. That's the same thing. So now the question is, well, what is arc sine of root 2 over 2? If you don't know this by heart, the idea is go back to a question about not inverse, but straightforward trigonometric functions. We know that an inverse trig function gives us an angle. So suppose you call this theta. Well, let's get rid of the arc sine by taking sine on both sides. So sine of theta will be the sine of arc sine of root 2 over 2, but sine of arc sine cancels, and we're left with root 2 over 2. And you see now we're asking the same question, but in a slightly different fashion. Here we're saying, what is arc sine of root 2 over 2? We call this theta, and here we're asking, okay, give me an angle, theta, at which sine of this angle is root 2 over 2. And if you remember, sine is root 2 over 2 exactly when the angle is pi over 4. So arc sine of root 2 over 2, that's just pi over 4. So we now have the coordinates of our point. The point on our curve is given by x is 1/2 and y is pi over 4. Well, now if we want the equation of the tangent line, as always it's just the equation of a line, so we write y equals mx plus b. As always, the slope of the tangent line is the derivative of the function at the point of interest, so let us differentiate arc sine of x. Arc sine, of root of x. So the derivative with respect to x of arc sine of root of x. Once again, here we have a composition, arc sine of root of x. The outside function is arc sine, and the derivative of arc sine, if you remember, is 1 over the square root of 1 minus the argument squared. And the argument here is root of x. But there's still a root of x left over, so we have to multiply what we have so far by the derivative of what's left over, which is root of x. And the derivative of root of x is 1 over 2 root of x. We can simplify this quite nicely. I'll write the 1 over 2 root of x first. And the root of x squared is simply x, so what we have here is root of 1 minus x. So now we have the derivative of our function, arc sine of root of x, for any given value of x. Well, the slope of the tangent line is the derivative of the function specifically at x equals 1 over 2. So now let's evaluate the derivative at 1/2, which will give us the slope of the tangent line at x equals 1 over 2. So the slope is just the derivative of our function, specifically at x equals 1/2. Let's see what we get here. We'll have 1 over 2 times the root of 1/2 times the root of, and here we have 1 minus 1/2. But 1 minus 1/2, that's just 1/2. Now think of what we have here. 1 over 2 times the root of 1/2 times the root of 1/2 is the root of 1/2 squared. The square root goes away, and all we are left with is 1/2. But 2 times 1/2 is 1, so we have 1 over 1, so it's just 1. So the slope of the tangent line at x equals 1/2 is just equal to 1. So the tangent line has equation y equals mx, but m is 1. So it's just y equals x plus b. And as always, to solve for b, we have to find, or use, I should say, the point that passes through the tangent line. And the point here is x equals 1/2, y equals pi over 4. So we make this substitution. So replacing y by pi over 4. And replacing x by 1/2. And we can solve for b by subtracting 1/2 on both sides of the equality. Therefore, b is quite simply pi over 4 minus 1/2. And if we want this as a single fraction, multiply this by 2 over 2, and you'll have pi minus 2 over 4. And we can conclude now with saying that the equation of the tangent line is x plus b, and b is pi minus 2 divided by 4. So there you have it. The tangent line to the function arc sine of root of x at the point x equals 1/2 is equal to x plus pi minus 2 over 4.